Welcome to This Explainer. Today, we're diving into a hidden, totally unseen force that dictates literally almost every single aspect of how our world operates. Yep, we're talking about friction. And more importantly, we're looking at the fascinating science of lubrication that we use to conquer it. I know it might sound like a kind of mundane concept at first, but as you're going to see, it's actually the silent guardian of everything from your own biology right up to global climate change policy. So, just to put things into perspective, I want you to imagine a pretty catastrophic scenario. What would happen if, at this exact moment, every single form of lubrication on Earth just vanished? Well, instantly, the joints in your knees and elbows would start to grind together painfully, bone on bone. Out on the streets, every car engine would seize up within seconds. In factories, massive industrial machines would literally screech to a halt, overheating and fusing together. It would be total global paralysis. That's the sheer, mind-boggling power of the topic we're unpacking today.
Okay, let's dive into this. Here's our roadmap for today. We'll start with the body's built-in oil, then move to medical and personal care, keeping heavy industry moving, solid lubricants for extremes, the global cost of friction, and finally, a sustainable, safer future.
Section 1. The body's built-in oil. How our own anatomy conquers friction.
You know, the battle against friction doesn't actually start in a massive factory or a car engine. It begins right inside our own bodies. Whenever two bones meet and move, like in your knees, your hips, or your fingers, they're protected by something called synovial fluid. Your body makes this joint fluid naturally from blood plasma. It contains proteins, enzymes, and hyaluronic acid, which gives it this thick, slippery consistency that strongly resembles egg whites. But please, don't try cooking with it. It acts exactly like motor oil in a car engine. It surrounds the joint, stopping the bones from rubbing together and causing damage. But get this, it does something motor oil can't do. It actively transfers vital nutrients from your body directly into the cartilage and surrounding tissues. So it's basically keeping the whole system nourished and functional all at once.
Section 2. Medical and personal care. Comfort, safety, and saving lives. Zooming out just a bit from natural biology, when we manufacture our own personal lubricants, understanding the chemistry is absolutely vital for your safety. The crucial point here is the difference between base formulas. Water and silicone-based lubricants are essential because they moisturize sensitive tissues without causing irritation, and, crucially, they maintain the integrity of latex condoms. On the flip side, oil-based lubricants like petroleum jelly or massage oils can actively break down and weaken latex. That's a huge deal because it can lead to condom breakage, severely increasing the risk of unintended pregnancies or sexually transmitted infections. So chemistry definitely matters here.
And over in a clinical setting, these fluids are just as critical. Sterile, non-toxic medical lubricants provide a super important barrier to protect delicate internal tissues from trauma. Just think about a catheter insertion, an endoscopy, or placing a feeding tube. Without medical-grade gels, these procedures would cause severe friction and terrible tissue damage. But what's truly amazing is how we've engineered these lubricants to multitask. For example, we now use lidocaine-infused gels that act as a mild anesthetic to actively relieve pain during procedures. We even have chlorhexidine-infused gels offering antimicrobial protection to aggressively reduce the risk of infection right at the site of contact. Talk about a multitasker, right?
Section 3. Keeping heavy industry moving. The fluids powering global manufacturing.
Okay, leaving the hospital and stepping into a manufacturing plant, the environment gets incredibly hostile. And this brilliantly illustrates a key point. Not all industrial fluids are just there to make things slippery. They actually serve entirely different mechanical purposes. Standard lubricants? Sure, they reduce friction on high-stress gears and bearings. But look at hydraulic fluids. Their primary job isn't actually lubrication at all. It's to transmit immense power and force through a fluid medium to operate heavy excavators and massive presses. Then you've got cutting oils, which are just indispensable in metalworking. When you're milling or drilling solid steel, the friction generates so much heat it can actually warp the metal or shatter the drill bit. Cutting oils step in to dissipate that heat while lubricating the cut. Finally, rust preventatives create a protective barrier to stop moisture from corroding metal parts during transport. Obviously, using the wrong fluid here, like, say, dumping cutting oil into a hydraulic press, would lead to a very expensive, immediate, and total machine failure. No way you want to mix those up.
Section 4. Solid lubricants for extremes. Surviving where liquids boil away.
So what happens in environments like deep space exploration or, inside a blast furnace where traditional liquid oils and greases would instantly boil, freeze, or catch fire? Well, this is where the mind-bending physics of solid lubricants comes in. These materials operate in what's called the boundary regime, forming a microscopic tribal film directly on a surface. They work because they're lamellar materials, meaning they're built in atomically thin planes. Within a single layer, the atomic bonds are incredibly strong. But between the separate layers, they're held together by extremely weak bonds known as van der Waals forces. Imagine trying to sprint across a hardwood floor covered in 1,000 playing cards. The cards effortlessly slip and shear right past one another, taking all the friction out of your movement. That is exactly what's happening at the atomic level.
There are a few major players in this extreme space. Graphite is highly common, but interestingly, it actually requires environmental moisture to work effectively. Molybdenum disulfide, or moly, is the absolute go-to for high-load mining equipment because it can withstand immense pressure and temperatures up to 400 degrees Celsius. Then there's boron nitride, which is highly resistant to thermal shock, making it perfect for things like furnace doors. Fluoropolymers, like PTFE, work a bit differently. Their atoms are just so tightly packed they naturally repel and slip past one another. And in space, because liquids would instantly boil away in a vacuum, we actually ionize and sputter dry lubricants directly onto the metal parts of satellites and Mars landers before they ever even leave Earth. How cool is that?
Section 5. The global cost of friction. The staggering energy toll of tribological contacts.
Now shifting our perspective to the macro scale, let's look at this staggering global picture. Research indicates that nearly a quarter, 23%, of the entire world's total energy consumption originates from tribological contacts. That is 119 exajoules of energy. To break that down, a massive 20% of all global energy is used purely to overcome friction, literally just fighting the resistance of parts moving against each other. Another 3% of global energy is spent strictly on remanufacturing worn parts and replacing equipment that failed simply because of wear and tear.
And that brings us to this absolutely massive number, 450 billion. If we implemented advanced, modern tribological technologies, we're talking better surface materials, superior solid and liquid lubricants, across our vehicles, machinery, and power generation, the impact would be world-changing. In the short term, over just 8 years, we could unlock 450 billion euros in global cost savings. And even more importantly for our climate, reducing that friction would prevent 1,460 megatons of CO2 emissions from entering the atmosphere. In fact, unlocking these technologies could save almost 9% of our total global energy consumption. That's a real game changer.
Section 6. A sustainable, safer future. Regulating the environmental impact of chemicals.
Now, as we push for highly advanced synthetic lubricants to save all that energy, governments are simultaneously having to reckon with the environmental legacy of industrial chemicals. A major focus right now is on PFAS. You've probably heard them called forever chemicals. They've historically been used across a ton of industries, including in some high-performance synthetic fluids and sealants, mostly because of their incredible resistance to heat and wear. But notice the aggressive timeline here of recent actions from the U.S. Environmental Protection Agency to regulate these substances. In October 2023, the EPA enacted a rule requiring massive historic reporting from manufacturers regarding their PFAS usage over the last decade. By January 2024, they expanded the toxics release inventory to include more of these chemicals. And then in April 2024, the EPA took 2 massive steps. First, designating 2 widely used PFAS as hazardous substances under the Superfund law to force cleanups, and second, issuing the first ever legally enforceable national drinking water standard to limit human exposure to these chemicals.
Which brings us to our final thought. We started out with the pretty simple concept of slippery fluids and ended up uncovering how mastering the microscopic space between atoms can literally save hundreds of billions of dollars and dramatically cut global carbon emissions. It really makes you wonder, doesn't it? If conquering microscopic friction can unlock that massive $450 billion in energy savings and almost 9% of our total global energy, what other unseen, silent forces are quietly dictating the rules of our world, just waiting for us to understand them? Thank you so much for joining me for this explainer. I really hope it completely changed the way you look at the mechanics of our everyday lives.